This is what happens when the sun goes inside a black hole, simulated in JavaScript using WebGL. You probably heard that black holes are crazy objects with gravity so strong even light can't escape. And sun is an uncontainable ball of energy that powers our entire existence. But no matter how crazy you think these things are, you're wrong, they're crazier. Let me show you what happens when an unstoppable star meets an inescapable object using real physics equation to simulate this effect in space. Let's start with gravity. We know it's how mass and energy bend space-time. This is Einstein's field equations. Think of it as a rulebook that tells space-time how to bend around mass and energy. These equations are insanely hard and complicated. Even Einstein didn't think anyone would solve them for years. Then, 3 weeks later, Carl Schwarzschild solved it. From a solution, we find out that for any given mass, there is a specific distance from it where gravity becomes so strong that not even light can escape. This distance is known as Schwarzschild radius, and for us, it gives the event horizon. I started by creating a blank window, basically just empty space where our simulation is going to be in. Then I added the event horizon, basically a pitch black sphere using the Schwarzschild radius as its size, and I added some rotation to it. Around the black hole, there is a glowing ring of photons orbiting at exactly 1.5 times the Schwarzschild radius. Let's see how we can make this. But first, I need to explain shaders to you. Think of shaders as tiny programs that runs in your GPU and decide how each pixel looks on screen. With my shaders, I drew a flat plane that always faces the camera. And my shaders check how far it's from the center. If it's 1.5 times the Schwarzschild radius, it glows bright. Otherwise, it fades away. Black holes are in this calm. Around them, there is gas, dust, and ripped apart stars, all smashing into each other and heating up, and the hottest parts glow blue. This ring of death is called the accretion disk. So I drew a disk and used my shaders to pick the color based on the actual temperature of the black hole. But it still doesn't have that black hole look yet. So here is what it's actually missing. The black hole's gravity is so strong, it doesn't just pull on stuff, it pulls on light. Light coming from the far side of the disk can't travel in a straight line anymore, it gets bent. So you end up seeing the back of the disk, the part that should be hidden behind the black hole, wrapping over the top. And the bottom shows up underneath. The whole thing folds on itself. This effect has a name, gravitational lensing, and every black hole in the universe does it. So I implemented this using some more of the traders magic from before. You really don't need to know the ins and outs of it since this is a setup for our actual simulation. Finally, that was a lot of physics and code. If that was confusing to you, don't worry. This is where our main simulation starts. We have our black hole now. Boys, now it's time to kill a star. Before that, let's rewind to gravity again. This is Newton's law of gravity. We'll use this to figure out how strongly the star accelerates towards the black hole. Now, let's add the star and give it some gravity. Every frame, I get the star's distance from the black hole. Then, use Newton's gravity equation to calculate acceleration. The acceleration changes velocity, and the velocity changes the position, and the whole loop repeats again. We can see our star going into the black hole. There is a specific distance from the black hole where the sun can't hold on to its own gravity. Beyond it, the black hole wins and rips apart the star. This exact distance is called the tidal radius. This is the formula to find out the tidal radius, where r star is the radius of the star, and this part is the mass of the black hole divided by the mass of the star, whole raised to 1/3. And in this case, mass of the black hole is 1 million times heavier than the mass of the star. So as you can see, the tidal radius is 100 times the sun radius. When the star's distance becomes smaller than the tidal radius, the code switches the star states into stretching, which is the next step. As the sun approaches the tidal radius, the near side of the star feels more gravity than the far side, and this makes the star get stretched. As the star gets closer, I slowly stretch it in the direction of the black hole and squeeze the sides. It goes from round to egg-shaped to a long stretched oval. And yeah, the actual scientific name is called spaghettification. Stephen Hawking named it. After crossing the tidal radius, the star can't hold itself together anymore. It turns into a stream of stellar plasma. I built this as thousands of individual particles, each representing a chunk of the plasma. Then I gave every single one of those 6,000 particles Newton's law of gravity, calculating it 6,000 times per frame. The near particles accelerate way harder than the far ones because the equation is 1/r squared, half the distance, 4 times the pull. This is the last step. We need to calculate each particle's orbital energy to figure out how much of the star can actually escape the black hole. This is the equation to figure out the orbital energy of each particle. If the energy is positive, they can escape. If not, they get sucked in. I run the same equation on every particle using its position and speed, and some fall in and some escape. And this phenomena is actually called the Higgs mechanism. That's it. Let's see the final result.